explore worlds where diamonds rain from carbon skies, and confront discoveries so strange that scientists are questioning whether our entire model of reality is broken. If you enjoy this journey, hit like and subscribe. Now, prepare yourself. We begin. 290 million years after the Big Bang, something impossible appeared. A galaxy, fully formed, bright, chemically complex. Scientists have confirmed its existence using the most powerful telescope ever built. They named it after a sacred river in the Himalayas, and it breaks nearly every rule we thought governed the early universe. To understand why this discovery sent shockwaves through the scientific community, you need to understand what we expected to find. The standard model of cosmology told us a clear story. After the Big Bang, the universe was a hot, chaotic soup of particles. Gravity slowly pulled matter together over hundreds of millions of years. The first galaxies were supposed to be small, messy, irregular clumps. They would take billions of years to organize into the beautiful spiral structures we see today. Our own galaxy, the Milky Way, took roughly 10 billion years to develop its sweeping spiral arms. 10 billion years of collisions, mergers, and gradual organization. This distant galaxy did it in a few hundred million. When astronomers pointed the James Webb Space Telescope at a tiny patch of sky no bigger than a grain of sand held at arm's length, they found something that should not be there. The galaxy contained 10 billion stellar masses worth of material. It had already organized that material into a structured disk, and its chemistry revealed oxygen and other heavy elements that require multiple generations of stars to produce. Here is what makes this even stranger. Heavy elements like oxygen do not exist at the beginning. The Big Bang only created hydrogen, helium, and trace amounts of lithium. Everything else, every atom of carbon in your body, every molecule of oxygen you breathe, was forged inside stars and scattered into space when those stars exploded. For a galaxy to contain significant oxygen, stars must have already lived and died, multiple generations of them. Yet this galaxy existed when the universe was only 2% of its current age. The implications are staggering. Either stars formed and died much faster than we believed possible, or something about our understanding of the early universe is fundamentally wrong. Scientists working on this discovery have called it extraordinary. They used 9 days of telescope time to gather the data. 167 hours of imaging focused on a patch of sky, so small that if they had pointed the telescope just a fraction of a degree in any direction, they would have missed it entirely. Think about that. This galaxy was found by accident, in a tiny random sample. If such a mature galaxy exists in such a small slice of sky, how many more are out there? The math suggests there should be many, and that terrifies cosmologists. The team that made this discovery was not looking for trouble. They were conducting a deep survey called the James Webb Space Telescope Advanced Deep Extragalactic Survey. They expected to find primitive, chaotic structures. Instead, they found a galaxy that looked like a younger twin of our own cosmic home. One researcher described it this way. Imagine expecting to find a newborn infant and instead discovering a fully grown adult. The physics of growth simply do not allow for that, unless the physics is wrong. This is confirmed science, published in peer-reviewed journals. The galaxy exists, its chemistry is real, and it forces us to confront an uncomfortable truth. The universe was capable of far more rapid assembly than anyone anticipated. Somehow, matter organized itself with breathtaking speed in the cosmic dawn. But here's what keeps astronomers awake at night. This galaxy is not alone. It is not even the strangest thing the telescope has found. Across the early universe, scattered through image after image, observers notice something even more puzzling. Tiny red points of light, hundreds of them. Objects so compact and so bright that no existing theory could explain them. And when scientists finally figured out what they were, it changed everything we thought we knew about black holes. In the summer of 2022, the James Webb Space Telescope sent back its first scientific images. Within weeks, astronomers noticed something strange. Scattered throughout the observations, appearing in nearly every deep field image, were tiny red points of light, small, compact, unusually bright, and completely unexplained. Scientists gave them a simple name, little red dots. At first, researchers assumed they were distant galaxies, Old galaxies tend to appear red because their stars have aged. The light from ancient stellar populations shifts toward warmer colors as the hot blue stars die off and leave behind cooler red ones. This is well understood physics. But something did not fit. These objects were too small. When astronomers tried to resolve them into recognizable galaxy shapes, they could not. The little red dots remained stubbornly compact. They appeared to be less than 2% the diameter of the Milky Way. If they were galaxies packed with enough stars to explain their brightness, those stars would need to be crammed together at impossible densities. The night sky of such a galaxy would be dazzlingly bright. You would see millions of stars with your naked eye. The stellar density would violate everything we know about how gravity organizes matter. So the mystery deepened. What were these objects? One possibility emerged quickly. Perhaps the light was not coming from countless stars, but from a single source, a supermassive black hole. When black holes feed on surrounding gas, they can outshine entire galaxies. The matter spiraling into the black hole gets compressed and heated to millions of degrees, producing enormous amounts of radiation. This explanation seemed promising. It would account for the brightness without requiring impossible star densities, but it created a new problem. Supermassive black holes that active should blast out X-rays and radio waves. Astronomers looked for those signals. They found almost nothing. The little red dots defied every category. Too bright to be normal galaxies, too quiet to be typical active black holes. They existed in a strange middle ground that our models could not explain. And there were so many of them. Hundreds have now been identified. They appear abundantly in observations of the early universe from around 400 million to 1 billion years after the Big Bang. Then, mysteriously, they seem to vanish from the cosmic record. Whatever these objects are, they existed for a brief window of cosmic time. They appeared suddenly, remained visible for perhaps 500 million years, and then disappeared. For 3 years, astronomers argued about their nature. Some favored the idea that they were dust-shrouded galaxies. Others insisted they must contain hidden black holes. The debate grew heated. Competing theories multiplied. But without better data, no one could prove anything conclusively. Then, in early 2025, researchers at the University of Copenhagen announced a breakthrough. They had analyzed the little red dots for 2 years, using the most detailed spectroscopic data available. Their conclusion was startling. The little red dots are young black holes, but not the kind anyone expected. These black holes are wrapped in dense cocoons of ionized gas. They are actively consuming that gas, generating enormous heat that shines through the cocoon. The radiation passing through gives them their distinctive red color, and the cocoon makes them appear far more massive than they actually are. The researchers found these black holes are about 100 times less massive than previous estimates suggested. They are not billion solar mass monsters. They are smaller, hungrier, and growing fast. This discovery solves one puzzle, but opens another. If these are young black holes in a feeding frenzy, we may be watching the birth of the supermassive black holes that anchor every major galaxy today. We are seeing cosmic infants in their growth spurt. But some scientists believe the truth is even stranger. They think the little red dots might not be simple black holes at all. They might be something that has never been seen before. What if the little red dots are not galaxies? What if they are not typical black holes either? What if they are something completely new? In late 2025, researchers proposed a radical idea. The mysterious red objects scattered across the early universe might be an entirely new type of cosmic structure. They called them black hole stars. The concept is as strange as it sounds. Imagine a black hole sitting at the center of an enormous sphere of hot, dense gas. The black hole is actively pulling matter inward. As gas falls toward the event horizon, it accelerates to incredible speeds. The compression generates temperatures of millions of degrees. This releases staggering amounts of energy. But here is the critical part. Only a tiny fraction of the infalling gas actually crosses the event horizon and disappears forever. Most of it gets blasted back out. The intense radiation pushes the majority of the material away from the black hole before it can be swallowed. Scientists sometimes describe black holes as messy eaters. They consume far less than they appear to grab. The rejected gas forms a dense, turbulent atmosphere surrounding the black hole. From a distance, this entire structure, the black hole plus its gas envelope, looks like a single, gigantic star. except it is not powered by nuclear fusion like normal stars. It is powered by gravity and the violent compression of infalling matter. One research team analyzed a particularly extreme little red dot they nicknamed the Cliff. Its spectrum showed something unprecedented. The object appeared to have so much atmosphere that it could not be explained as a collection of ordinary stars. It seemed to be one gigantic, very cold star. But it was not cold because it lacked energy. The coldness came from the gas envelope surrounding the black hole. The dense cocoon absorbs the highest energy radiation and re-emits it at longer wavelengths, making the object appear red and relatively cool on the surface, even while tremendous heat rages at its core. If this interpretation is correct, we have discovered a missing link in cosmic evolution. Here is why this matters. Astronomers have long wondered how supermassive black holes grow so massive so quickly. Normal feeding processes should take billions of years, but we find billion solar mass black holes existing less than a billion years after the Big Bang. The math does not work. Black hole stars might solve this problem. If young black holes can wrap themselves in dense gas cocoons, they can feed much faster than exposed black holes. The cocoon shields the growing black hole from its own radiation, allowing it to consume material more efficiently. The gas provides the fuel, the black hole grows, and over several 100 million years, it can balloon from a modest seed into a cosmic giant. This would explain something else that puzzled astronomers. The little red dots appear everywhere in the early universe, but vanish about a billion years after the Big Bang. If they represent a temporary phase of black hole growth, that makes sense. The cocoon eventually gets consumed or blown away. The feeding frenzy ends, and what remains is a mature, supermassive black hole sitting quietly at the center of a galaxy. We would never see the black hole star phase in the modern universe because that stage ended billions of years ago. The James Webb Space Telescope is looking back in time, catching these objects during their brief but crucial growth period. This is still a theory. Scientists are debating it intensely. More observations are needed to confirm whether black hole stars truly exist. But the evidence is compelling. The spectral signatures, the size, the brightness, the timing, everything fits. If confirmed, this discovery would reshape our understanding of how galaxies form. The supermassive black holes at the centers of galaxies would not be passengers that grew alongside their hosts. They would be the seeds around which galaxies assembled. But the strangeness does not stop there. Even setting aside the little red dots, astronomers found something else troubling in the early universe. Galaxies that are simply too big. The universe has a speed limit for growth, or so we believed. When the James Webb Space Telescope began surveying the distant cosmos, it revealed galaxies far larger and more luminous than any model predicted. These were not subtle outliers. They were 10 to 100 times more massive than the physics should allow. To grasp why this is a crisis, consider how galaxies are supposed to form. After the Big Bang, the universe was almost perfectly smooth. Matter was spread nearly evenly in all directions, but not quite perfectly. Tiny quantum fluctuations during the first fraction of a second created microscopic variations in density. Some regions had slightly more matter than others. Gravity amplified these differences over time. Denser regions pulled in more material, growing slowly but steadily. The first dark matter halos formed. Gas collected within these halos. Stars ignited. Gradually, over hundreds of millions of years, the earliest galaxies assembled. The key word is gradually. The standard cosmological model predicts a specific rate of growth. Matter can only accumulate so fast because gravity operates at a fixed strength, and the universe was expanding, working against the pull of gravity. According to these calculations, the first billion years should have produced small, faint, chaotic structures. Finding anything as bright and organized as the modern Milky Way should be impossible until several billion years had passed. The telescope disagreed. In its first year of observations, the James Webb Space Telescope found bright galaxies everywhere in the early universe. Not just a few anomalies, but a consistent population of objects that challenged expectations. Some appeared as luminous as mature galaxies, despite existing when the universe was only 3% of its current age. The initial reaction was disbelief. Many astronomers assumed the measurements were wrong. Perhaps the telescope's instruments needed better calibration. Perhaps the distance estimates were incorrect. placing nearby objects at cosmic distances. Teams around the world scrutinized the data. They recalibrated. They reanalyzed. The results held. One particularly dramatic example was a galaxy found at a redshift, indicating we see it as it appeared just 400 million years after the Big Bang. It contained billions of stellar masses worth of stars. For context, our own galaxy contains roughly 200 billion stars, but took over 13 billion years to assemble them. How can a galaxy accumulate so much material so quickly? Several explanations have been proposed. Perhaps star formation was more efficient in the early universe. Perhaps the first stars were more massive and luminous, making young galaxies appear brighter than their actual mass would suggest. Perhaps dark matter behaved differently at early times. Each explanation has problems. Higher star formation efficiency requires conditions we do not observe elsewhere. More massive early stars would leave distinct chemical signatures that we have not found. Modified dark matter would conflict with other observations. Some researchers wondered if the discovery meant the Big Bang happened earlier than we thought. If the universe were older, there would be more time for growth. But the cosmic microwave background radiation, the afterglow of the Big Bang, provides an extremely precise age estimate. The universe is 13.8 billion years old. This is not negotiable. So we face a genuine puzzle. The universe produced large, bright, mature galaxies far faster than our models allow. Either something accelerated growth in ways we do not understand, or our models are missing something fundamental. And the crisis extends beyond galaxies. The same observations that revealed impossibly massive galaxies also revealed something even more disturbing. Supermassive black holes that dwarf their host galaxies. Objects so oversized that they break a relationship astronomers thought was universal. The rules are failing, and no one knows why. Spiral galaxies are supposed to be old. The beautiful pinwheel structures we see in images of nearby galaxies represent billions of years of evolution. Our own Milky Way took roughly 10 billion years to develop its graceful spiral arms. The process requires time, stability, and the right conditions. First, a galaxy must accumulate enough mass. Then it must settle into a rotating disk. Density waves must propagate through that disk, compressing gas and triggering star formation along curved paths. Gradually, over cosmic ages, the spiral pattern emerges. This is settled science. Dozens of simulations confirm the timeline. Spiral structure requires patience. So, when astronomers found a fully formed spiral galaxy just 1.5 billion years after the Big Bang, they did not know what to say. The galaxy is called Alaknanda, named after a river in the Himalayas that is one of the twin sources of the sacred Ganga River. The name carries deep meaning. In Hindi, Mandakini, the other twin source, is also the word for the Milky Way. Alaknanda looks shockingly like our cosmic home. It has sweeping spiral arms, a defined disk structure, and rapid star formation concentrated along the spiral pattern. These are features astronomers associate with mature, evolved systems, not with galaxies existing when the universe was roughly a tenth of its current age. The discovery was made possible by gravitational lensing. A massive cluster of galaxies sits between Earth and Alaknanda. The cluster's gravity bends and magnifies the light from the distant spiral, acting like a cosmic magnifying glass. Without this natural amplification, the galaxy would be too faint to study in detail. Using this magnified view, researchers examined Alaknanda with unprecedented clarity. They confirmed the spiral arms are real, not an artifact of distorted light. They measured the rotation of gas and stars. They calculated the total mass. The galaxy contains roughly 10 billion stellar masses. It assembled and organized this material into a beautiful spiral disk in just a few 100 million years. By cosmic standards, that is extraordinarily fast. The team that made this discovery described their findings carefully. They noted that the early universe was capable of far more rapid galaxy assembly than anyone anticipated. Somehow, this galaxy pulled together enormous amounts of material and organized it into stable structures almost immediately. But how? One possibility involves cold gas flows. If steady streams of cold gas funneled into the young galaxy without violent disruptions, density waves could have established themselves quickly. The galaxy would have had fuel for rapid star formation and the smooth conditions needed for spiral arms to develop. Another possibility is more unsettling. Perhaps spiral galaxies do not require as much time as we thought. Perhaps our simulations are missing something about the physics of galaxy formation. Alaknanda is not alone. The James Webb Space Telescope has found several surprisingly mature disk galaxies at great distances. These objects keep appearing, challenging the narrative that early galaxies were chaotic and irregular. One massive spiral, nicknamed the Big Wheel, existed within the first 2 billion years of the universe. Its structure is so clean and organized that researchers expected it to be elliptical, a smooth blob of stars. Instead, it displays beautiful spiral arms, similar to those in our local neighborhood. The implications ripple outward. If galaxies can form and mature this quickly, what else might the early universe have accomplished? The answer involves objects at the very hearts of these galaxies, objects that are even more out of place than the galaxies themselves. Supermassive black holes, growing without restraint. At the center of nearly every large galaxy sits a monster. Supermassive black holes contain millions or even billions of times the mass of our star. They anchor galaxies, influence star formation across thousands of light years, and when they feed, they can outshine everything around them. In the nearby universe, these black holes follow a pattern. The mass of the central black hole scales predictably with the mass of its host galaxy. Bigger galaxies have bigger black holes. The ratio is remarkably consistent. For every 1,000 units of stellar mass, there is roughly 1 unit of black hole mass. This relationship suggests that galaxies and their black holes grow together, evolving in lockstep over cosmic time. The physics seems to enforce a balance. When the black hole grows too fast, its radiation heats surrounding gas and slows star formation. When stars form too quickly, they consume the gas the black hole needs to feed. This elegant dance was considered one of the best understood aspects of galaxy evolution. Then the James Webb Space Telescope looked at the early universe. What it found broke the pattern completely. In distant galaxies, supermassive black holes are oversized, dramatically oversized. Instead of a 1,000-to-1 ratio between stellar mass and black hole mass, astronomers found ratios of 100-to-1, sometimes 10-to-1. In extreme cases, the black hole mass equaled the total stellar mass of its host galaxy. These black holes are not slightly larger than expected. They are 10 to 100 times more massive than the relationship predicts. A team led by researchers at Harvard and the Smithsonian analyzed 21 supermassive black holes in galaxies ranging from 12 to 13 billion light-years away. Each one violated the local scaling relationship. The statistical analysis confirmed this was not a fluke. These early black holes are genuinely overmassive relative to their host galaxies. The discovery creates a profound puzzle. How did these black holes grow so large while their galaxies stayed small? One explanation involves timing. Perhaps in the early universe, black holes grew first and galaxies assembled later. The black holes would have consumed available gas before stars could form, keeping galaxies small while the black holes ballooned. But this raises new questions. What created such massive black hole seeds in the first place? Normal stellar collapse produces black holes of perhaps a few dozen solar masses. Growing from there to millions or billions of solar masses through feeding alone would take longer than the universe's age at that time. Some researchers propose that the first black holes formed through direct collapse. Instead of starting as stellar remnants, they emerged when enormous gas clouds collapsed directly into black holes without ever becoming stars. This would create heavy seeds, perhaps 100,000 solar masses or more, giving the black holes a head start. The James Webb observations support this theory. If black holes started massive and grew faster than their galaxies, the oversized ratios make sense. Over billions of years, the galaxies would catch up, establishing the balanced relationship we see today. But confirming this requires finding even smaller black holes at even greater distances. If heavy seeds are real, there should be a population of intermediate objects between the primordial seeds and the monsters we observe. The telescope continues searching. Each observation pushes deeper into cosmic history. Each discovery reveals more black holes that should not exist. And among these impossible objects, scientists found one that defied every limit, a black hole eating faster than physics allows. Every black hole has a speed limit, As matter falls toward a black hole, it compresses and heats up. The resulting radiation pushes outward against the infalling material. At some point, the outward pressure from radiation equals the inward pull of gravity. This balance point is called the Eddington limit. Beyond this limit, a black hole cannot consume more material. The radiation it produces blows away the food before it can be swallowed. The black hole effectively chokes on its own brightness. This limit is fundamental. It emerges from basic physics, and it sets a maximum speed for black hole growth. Even feeding continuously at the Eddington limit, a black hole takes hundreds of millions of years to grow substantially. In November 2024, astronomers announced they had found something that appeared to violate this limit spectacularly. Using the James Webb Space Telescope, researchers examined an ancient galaxy known to host an intense X-ray source. The galaxy existed just 1.5 billion years after the Big Bang. At its center was a supermassive black hole in a feeding frenzy. The data showed outflows of gas unlike anything ever observed. The speed and scale of these outflows indicated the black hole was consuming matter at more than 40 times its Eddington limit. 40 times. Not a small excess. A massive violation of what physics says is possible. If accurate, this single feeding episode could explain most of the black hole's observed mass. Instead of growing steadily over billions of years, it might have bulked up in a cosmic instant. The discovery triggered excitement and skepticism in equal measure. Some researchers saw it as evidence for a completely new feeding mechanism. Others suspected something was wrong with the measurements. In early 2025, a different team revisited the data. They found the original measurements had been distorted by dust. Dust absorbs and scatters light, dimming the signal that reaches our telescopes. If you do not account for dust properly, you can dramatically underestimate a black hole's true mass and misinterpret its feeding rate. When the team corrected for dust extinction, the picture changed. The black hole was not eating at 40 times the Eddington limit. It was feeding at a rate consistent with the theoretical maximum. Still impressive, but not physics-breaking. This correction sounds like the end of the story. The extreme claim turned out to be a measurement error. Case closed. But the implications extend further. If dust misled astronomers in this case, it might be misleading them in many others. The newly discovered class of objects called little red dots are all surrounded by complex dust environments. Their true properties might be systematically mismeasured. Some black holes we think are impossibly massive might actually be smaller. Some we think are feeding normally might be growing faster than we realize. The lesson is humbling. Even with the most powerful telescope ever built, interpreting signals from the early universe remains extraordinarily difficult. Dust, distance, and cosmic expansion all distort what we see. Scientists must remain cautious. Every extraordinary claim requires extraordinary verification. But one discovery from the James Webb Telescope required no correction. One object was so dramatic, so undeniable, that its very existence validated 50 years of theoretical predictions. A supermassive black hole ejected from its own galaxy, now racing through space faster than almost any object ever observed. Something enormous is tearing through space. A supermassive black hole weighing 20 million times the mass of our star. Moving at 2.2 million miles per hour, trailing a 200,000 light-year wake of newborn stars behind it. This is not science fiction. This is confirmed observation. The James Webb Space Telescope has provided the definitive evidence. Scientists first noticed something strange in 2023 while examining images from the Hubble Space Telescope. They saw a thin line extending from the center of a distant galaxy. At first, they thought it might be an artifact, a glitch in the camera or a cosmic ray strike, but the line persisted in multiple observations. It was real, and it was connected to the galaxy's core. The team hypothesized they were seeing the wake of a runaway supermassive black hole, a black hole ejected from its galaxy, plowing through surrounding gas, compressing material ahead of it and leaving a trail of star formation behind. Skeptics offered alternative explanations. Perhaps it was a shredded dwarf galaxy, perhaps an edge-on disk seen at just the right angle. The evidence was suggestive but not conclusive. Then the James Webb Space Telescope provided the proof. Using its near-infrared spectrograph, the telescope did not just image the object, it measured motion. It analyzed how fast gas was moving at different points along the structure, and what it found removed all doubt. At the tip of the feature, there is a sharp velocity change. Gas suddenly jumps by roughly 600 kilometers per second over a distance of just 1 kiloparsec. This kind of abrupt kinematic discontinuity can only be caused by one thing: a supersonic bow shock. Something massive is pushing through the gas faster than sound waves can travel. It is compressing material in front of it, creating a shock front. Behind the shock, gas cools and collapses, forming new stars that stream out in a long tail. The black hole itself is invisible. Black holes do not emit light, but its effect on the surrounding environment screams its presence. The researchers calculated the black hole's velocity from the shock data: 954 kilometers per second, plus or minus about 100. This is nearly 1,000 kilometers per second, or roughly 2.2 million miles per hour. For perspective, Earth orbits its star at about 67,000 miles per hour. This black hole is moving 30 times faster. At this speed, the black hole will escape its galaxy entirely. It will never return. It will wander through intergalactic space forever, a cosmic exile. But how does something with the mass of 20 million stars get ejected from a galaxy? Two mechanisms can produce such enormous velocities. Both require extraordinary violence. The first involves a three-body interaction. If three supermassive black holes end up in the same galactic core, their gravitational dance can slingshot one member out at tremendous speed. The other two remain behind, bound in a shrinking orbit. The second involves gravitational waves. When two supermassive black holes merge, they release enormous energy in ripples through spacetime. If the merger is asymmetric, the burst of gravitational radiation can kick the newly formed black hole with enough force to escape. The team analyzing this runaway believes the merger scenario is most likely. The black hole's mass and velocity match predictions for a gravitational wave recoil kick. This discovery validates 50 years of theoretical work. Scientists predicted runaway supermassive black holes decades ago. Now, finally, we have seen one, and the galaxy left behind might have a strange future. A galaxy without a central supermassive black hole. We do not know what happens to such a system. We have never observed one. The runaway black hole did not come from nowhere. Its origin lies in a spectacular cosmic collision, two galaxies crashing together, their supermassive black holes spiraling toward each other, and the violent aftermath that sent one monster flying into the void. The host system is called the Cosmic Owl. It earned this name because of how it looks. Two ring galaxies approaching each other, their cores glowing brightly like a pair of eyes. The shape resembles an owl's face, staring back at observers across billions of light years. The cosmic owl lies roughly 8.8 billion light years away. At that distance, light takes nearly 9 billion years to reach us. We are seeing this system as it existed when the universe was less than 5 billion years old. Ring galaxies are already rare. They form when one galaxy punches through the center of another, sending ripples outward through the disk like a rock dropped in a pond. Finding two ring galaxies interacting with each other is extraordinary. But the cosmic owl contains something even more remarkable: that long linear feature extending from the system. The wake of the runaway supermassive black hole. Astronomers believe the sequence of events unfolded like this. Long ago, two separate galaxies existed. Each contained its own supermassive black hole. Perhaps they also contained additional black holes from previous mergers. These galaxies drifted closer together over millions of years, drawn by their mutual gravity. When galaxies collide, stars rarely hit other stars. Space is mostly empty. But the supermassive black holes at the galaxy centers sink toward each other. They orbit closer and closer, losing energy through gravitational interactions and eventually through gravitational wave radiation. In the cosmic owl system, something triggered an ejection. Either a three-body interaction flung one black hole outward, or two black holes merged asymmetrically, and the resulting recoil kick propelled the combined object away. The ejected black hole carried enormous momentum. It blasted through the surrounding gas at supersonic speed, compressing material ahead of it into a brilliant bow shock. Behind it, the compressed and cooling gas collapsed into new stars, creating a trail more than 60 kiloparsecs long. 60 kiloparsecs. That is roughly 200,000 light years. For comparison, The entire Milky Way is only about 100,000 light-years across. The wake behind this runaway black hole is twice the diameter of our entire galaxy. The James Webb observations captured the bow shock in unprecedented detail. The spectrum revealed signatures of fast radiative shocks and rapid cooling. The chemistry and velocity measurements matched predictions for a supersonic object plowing through diffuse gas. Everything points to one conclusion. A supermassive black hole was violently ejected from the cosmic owl and is now racing through space, leaving creation in its wake. This discovery has profound implications. If runaway supermassive black holes are real, there might be many more wandering through the universe. Some estimates suggest millions could be drifting through intergalactic space, invisible and undetectable unless they happen to pass through gas clouds dense enough to produce visible effects. The universe may be haunted by cosmic exiles, monsters roaming the darkness between galaxies. But the cosmic owl also raises questions about how supermassive black holes form in the first place. If they can be ejected, merged, and flung across the universe, their history must be more violent and chaotic than we imagined. Understanding this violence requires understanding how black holes are born, and the answer might involve seeds far heavier than anyone expected. Where do supermassive black holes come from? This question has haunted astronomers for decades. We see black holes containing billions of solar masses sitting at the centers of galaxies. We find them existing less than 1 billion years after the Big Bang. But standard physics cannot explain how they grew so massive so quickly. Normal black holes form when massive stars die. A star, perhaps 30 times the mass of our star, exhausts its nuclear fuel, collapses, and leaves behind a black hole of maybe 10 to 30 solar masses. This is well understood, but 10 solar masses is nothing compared to 1 billion. If you started with a stellar mass black hole and fed it continuously at the maximum possible rate, it would take billions of years to reach supermassive scales. Longer than the universe had existed when we observe these ancient monsters. Something is missing from the story. Two main theories have emerged. The first proposes that early black holes grew through extreme feeding episodes. Perhaps the first stars were giants, hundreds of times more massive than typical modern stars. When they died, they left behind larger black holes. Perhaps those black holes merged repeatedly, combining their masses. Perhaps feeding rates occasionally exceeded the theoretical limits. This theory requires special conditions. It requires a continuous supply of gas, few disruptions, and enough time for cumulative growth. The math is tight, but possible. The second theory proposes something more dramatic. What if the first black holes did not start small? What if they were born massive? This is the heavy seeds theory. Instead of forming from dead stars, the first black holes might have formed directly from collapsing gas clouds. No star phase, no gradual growth from tiny beginning, just a direct gravitational implosion that created black holes 100,000 times more massive than our star in a single event. The conditions for direct collapse are extreme. You need an enormous gas cloud, relatively free of the heavy elements that would otherwise cool the gas and fragment it into smaller clumps. You need the cloud to collapse uniformly, without forming stars along the way. These conditions might have existed in the very early universe. Before the first generations of stars scattered heavy elements everywhere, pristine gas clouds could have remained metal-free and vulnerable to direct collapse. The James Webb Space Telescope has provided the first observational evidence supporting heavy seeds. A team from the Massachusetts Institute of Technology examined 6 ancient quasars, galaxies with actively feeding supermassive black holes, using the telescope's infrared instruments. They measured the light from stars surrounding these black holes, something impossible with previous telescopes because the black hole's glare overwhelmed everything else. The data revealed something significant. In these early systems, the black holes appear to have gained their mass before their host galaxies did. The stellar populations are younger and less developed than expected if galaxies and black holes grew together. This supports the heavy seeds scenario. If black holes started massive and galaxies assembled around them later, we would expect exactly this pattern. The black hole arrives first, already enormous. The galaxy catches up over billions of years. One researcher described it this way. In the early universe, supermassive black holes might have gained their mass before their host galaxies did. The initial black hole seeds could have been more massive than anything we observe today. The implications are staggering. Supermassive black holes might not be passengers in galactic evolution. They might be the foundations upon which galaxies are built. But heavy seeds are still theoretical. We have not directly observed one forming. The evidence is circumstantial, based on the properties of the systems we can see. To truly understand the birth of black holes, we need to look even further back. We need to witness the very first light. For hundreds of millions of years after the Big Bang, the universe was dark. Not just dark in the sense of empty space. Dark because light could not travel freely. The entire cosmos was filled with neutral hydrogen gas, and neutral hydrogen absorbs most wavelengths of energetic light. Any photon trying to cross the universe would be swallowed almost immediately. This period is called the Cosmic Dark Ages. No stars, no galaxies, just a vast fog of primordial gas, slowly cooling, waiting for something to change. Then the first stars ignited. Their intense ultraviolet radiation began ionizing the surrounding hydrogen, stripping electrons from atoms, creating pockets of transparent ionized gas where light could finally travel freely. These ionized regions grew, they expanded, they merged with neighboring bubbles. Slowly, the fog cleared, and the universe transitioned from opaque to transparent. This transformation is called the epoch of reionization. Understanding when it started, how it proceeded, and which sources were responsible has been one of the central goals of modern cosmology. For decades, scientists believed reionization did not begin until the universe was roughly 500 million years old. The first galaxies needed time to form and produce enough radiation to make a difference. Then, the James Webb Space Telescope found something that rewrote the timeline. A galaxy called JADESGSZ131 sits at a redshift, indicating we see it just 330 million years after the Big Bang. That is remarkably early, but what makes this galaxy extraordinary is not its age. It is what the galaxy is doing to its surroundings. When astronomers examined the spectrum of this galaxy, they found a signature they did not expect, a powerful emission line from ionized hydrogen. The signal was so strong that it shone with the brightness of 10 billion stellar masses. This light should not have been visible. At such early times, the neutral gas surrounding galaxies should have absorbed it completely, unless the galaxy had already carved out an ionized bubble around itself. That is exactly what the data show. This tiny, ancient galaxy had already begun clearing the cosmic fog just 330 million years after the Big Bang. The researchers who made this discovery described it as witnessing the onset of reionization at redshift 13. No one had predicted it would happen this early. The finding has immediate implications. If reionization started earlier than believed, the first stars and galaxies must have formed earlier too. The timeline of cosmic history needs revision, but questions remain. What is producing the radiation that ionized this bubble? The first stars are thought to be extremely hot and ultraviolet bright, but another possibility exists: supermassive black holes. When black holes consume gas, they generate enormous amounts of X-ray and ultraviolet radiation. A young, actively feeding black hole could ionize surrounding gas as effectively as millions of stars. The galaxy with the earliest ionized bubble might contain one of the first black holes. Scientists are investigating. Either way, this discovery marks a milestone. We have caught the universe in the act of waking up. The long, dark ages are ending. Light is beginning to win. But the transition was not simple. The reionization of the universe unfolded in ways far more complex than anyone imagined. The epoch of reionization was not a single event. It was a process that unfolded over hundreds of millions of years, across billions of light years, in ways that varied dramatically from region to region. Some parts of the universe lit up early, others remained dark for much longer. The cosmic fog did not lift uniformly. It cleared in patches, driven by local sources of radiation, shaped by the distribution of matter and the accidents of structure formation. Understanding this patchwork transformation has been one of the greatest challenges in cosmology. Until recently, we could barely observe it. The distances involved pushed the limits of every telescope. The signals were faint, absorbed, distorted by billions of years of cosmic expansion. The James Webb Space Telescope changed everything. With its infrared sensitivity, and unprecedented resolution, the telescope can peer into the epoch of reionization and watch the process unfold. It can identify individual galaxies contributing to the ionizing radiation. It can map the boundaries between ionized bubbles and neutral fog. The emerging picture is both beautiful and chaotic. Reionization appears to have started much earlier than previously believed, perhaps around 300 million years after the Big Bang. But it did not complete until roughly 1.1 billion years after the Big Bang, more than 200 million years later than earlier estimates suggested. This extended timeline means the transformation was slow and uneven. Some galaxies were powerful enough to ionize their surroundings quickly, others were weak, making little impact. The neutral regions between bubbles persisted stubbornly, resisting the advance of light. One major discovery involved extremely faint dwarf galaxies. For years, astronomers debated which sources were primarily responsible for reionization. Massive galaxies seemed like obvious candidates because they produced tremendous amounts of radiation. But there are not that many massive galaxies in the early universe. Dwarf galaxies, on the other hand, are everywhere. They are small, faint, and individually weak, but their numbers are overwhelming. When scientists analyzed the cumulative radiation from all the dwarf galaxies the telescope could detect, they found something surprising. These tiny galaxies produced enough ionizing photons to transform the entire universe. The team that made this discovery emphasized its significance. Ultra-faint galaxies played a crucial role in the early universe's evolution. They produced the radiation that changed neutral hydrogen into ionized plasma. Understanding low-mass galaxies is essential to understanding cosmic history. This conclusion has implications beyond reionization. If small galaxies dominated the photon budget of the early universe, they also dominated star formation. The majority of stars that have ever existed might have been born in galaxies too faint for us to see individually. The universe we observe, the bright galaxies and dramatic structures, might represent only the visible tip of a vast iceberg. Beneath the surface, countless tiny systems have shaped cosmic history from the beginning. But reionization is not just about counting photons. The process had physical consequences that echo to the present day. When ionizing radiation flooded through the universe, it heated the gas between galaxies. This heating changed how matter could collapse and form new structures. Small gas clouds that might have become dwarf galaxies were instead evaporated away. Reionization did not just illuminate the universe, it sculpted it. It determined which structures could form and which could not. We are still living with the consequences, and we are still debating exactly how it happened. They are almost invisible, scattered across the early universe, too faint for most telescopes to detect, small enough to fit inside a single arm of the Milky Way. Dwarf galaxies, the runts of the cosmic litter. For decades, astronomers overlooked them when thinking about the big questions. How did the universe evolve? What drove the major transitions in cosmic history? The focus was always on the giants, the massive galaxies with billions of stars, the dramatic quasars with supermassive black holes blazing at their centers. But the James Webb Space Telescope revealed an uncomfortable truth. The giants were never the whole story. Perhaps they were never even the most important part. The telescope examined 8 of the faintest dwarf galaxies ever detected during the epoch of reionization. These objects existed when the universe was still transitioning from darkness to light, roughly 900 million years after the Big Bang. Despite their small size, these galaxies were producing ionizing radiation at remarkable rates. Their combined output was enough to account for a significant fraction of the photons needed to transform the universe. And these 8 galaxies were just a tiny sample from a tiny patch of sky. When astronomers extrapolated to the full population of dwarf galaxies throughout the observable universe, the numbers became staggering. Faint dwarf galaxies might have produced the majority of the ionizing radiation during reionization. They might have done most of the work in clearing the cosmic fog. This discovery inverts our understanding of cosmic evolution. The smallest structures had the biggest impact. The physics makes sense in retrospect. Dwarf galaxies form first in the hierarchical model of structure formation. They are abundant because small clumps of matter collapse before large ones, and their stars, though fewer in number, can be extremely hot and luminous in the early universe. Massive galaxies form later, through mergers of smaller systems. By the time they dominate the cosmic landscape, reionization is already complete. We were looking for the source of light in the wrong place. We focused on the brightest objects and missed the collective glow of countless dim ones. The lesson extends beyond astronomy. Sometimes the most significant changes come not from dramatic singular events, but from the accumulated effect of many small contributions. The universe teaches humility. But if dwarf galaxies drove reionization, we face a new challenge. These objects are extraordinarily difficult to study. Even the James Webb Space Telescope can only detect the brightest ones. The faintest members of the population remain invisible, their properties inferred rather than observed. Future telescopes may help. Larger mirrors, more sensitive instruments, and longer observation times could reveal the smallest galaxies in the early universe. Until then, we must work with incomplete data. The discovery also raises questions about what happened to these dwarf galaxies. We see their descendants in the local universe, small satellite galaxies orbiting larger ones like the Milky Way, but the numbers do not match perfectly. Some of the early dwarfs may have been destroyed, absorbed into larger galaxies, evaporated by the very radiation they helped produce. The universe that dwarf galaxies created might have turned against them. The ionizing light that ended the Dark Ages also heated intergalactic gas, preventing it from falling into small gravitational wells. Dwarf galaxies that formed before reionization could continue growing. Those that tried to form afterward found their fuel supply cut off. Reionization was not just a transition in visibility, it was a transformation of the conditions for cosmic structure formation, and its effects ripple forward through billions of years. The universe is expanding. This is not controversial. Since the 1920s, astronomers have known that distant galaxies are moving away from us. The farther away they are, the faster they recede. This expansion stretches space itself, carrying galaxies along like leaves on a flowing river. The rate of this expansion is measured by a number called the Hubble constant. Determining its precise value has been one of the central projects of modern cosmology, and it has led to one of the most frustrating puzzles in physics. There are two main ways to measure the Hubble constant. The first involves observing objects in the nearby universe. Astronomers identify stars with known intrinsic brightness, measure how bright they appear, and calculate their distance. By combining distances with recession velocities, they determine how fast space is expanding locally. The second method involves observing the cosmic microwave background, the afterglow of the Big Bang. This radiation carries information about the early universe. By analyzing its properties and applying the standard cosmological model, scientists can predict what the Hubble constant should be. These two methods should give the same answer. They do not. The nearby universe measurements consistently find expansion rates around 73 kilometers per second per megaparsec. The cosmic microwave background predictions give around 67 kilometers per second per megaparsec. The difference might seem small, but it is far larger than the measurement uncertainties allow. Both methods have been refined repeatedly over decades. The discrepancy persists. It even grows slightly as measurements improve. This disagreement is called the Hubble tension. And the James Webb Space Telescope just made it worse. Some astronomers hoped the tension was caused by measurement errors in the nearby universe observations. Previous telescopes, particularly the Hubble Space Telescope, struggled to resolve individual stars in distant galaxies. Perhaps blending of overlapping stars introduced systematic errors. The James Webb Space Telescope does not have this problem. Its resolution is dramatically sharper. It can cleanly separate stars that Hubble could not distinguish. When researchers reanalyzed the distance measurements using James Webb data, they found the previous results were correct. The expansion rate, measured in the nearby universe, remains around 73. The tension is real. This confirmation has profound implications. Either something is wrong with our measurements of the cosmic microwave background, or something is wrong with our cosmological model, or both. The standard model of cosmology, called lambda CDM, has explained observations successfully for decades. It describes a universe dominated by dark energy and cold dark matter, expanding according to Einstein's equations. It fits the cosmic microwave background beautifully, but it predicts a Hubble constant around 67. The universe appears to be expanding faster than this model allows. Something is missing. Cosmologists have proposed various solutions, Perhaps the early universe contained an additional component of energy that boosted expansion temporarily. Perhaps dark energy behaves differently than we assumed. Perhaps new physics is required. None of these proposals has gained universal acceptance. The tension remains unresolved, but one idea keeps appearing in discussions, a concept that might explain both the expansion problem and the puzzle of impossibly bright early galaxies. Early dark energy. What if two of cosmology's biggest puzzles have the same solution? The first puzzle is the Hubble tension. The universe expands faster than our standard model predicts. The second puzzle involves the early galaxies found by the James Webb Space Telescope. They are too massive and too luminous for their age. Standard models cannot explain how they grew so quickly. These puzzles seemed unrelated. One involves the expansion rate of space. The other involves the formation of structure within space. Different phenomena governed by different physics. But a team of physicists from the Massachusetts Institute of Technology realized the connection. They proposed that both anomalies could be explained by early dark energy. Dark energy is the name we give to whatever is accelerating the universe's expansion today. In the standard model, dark energy has a constant density throughout cosmic history. It does not change. It does not interact with matter in complex ways. But what if there was additional dark energy in the early universe? A temporary component that existed only during the first few 100 million years, then faded away. This early dark energy would have pushed the universe apart faster during its infancy. It would have stretched space more quickly than the standard model assumes. This accelerated early expansion would have several effects. It would change the balance of cosmological parameters. The seeds of structure formation would be slightly larger. Dark matter halos would grow faster. Galaxies would form earlier and brighter. The team tested this idea using sophisticated simulations. They incorporated a model of early dark energy that had been proposed to resolve the Hubble tension and asked what it would do to galaxy formation. The results were striking. With early dark energy, the skeletal structure of the early universe changes in subtle but important ways. The amplitude of density fluctuations increases. Dark matter halos become bigger. Galaxies form earlier and shine more brightly. The model predicted exactly what the James Webb Space Telescope observed: bright, massive galaxies appearing much sooner than standard cosmology allows. One researcher described the finding this way: "We demonstrated the potential of early dark energy as a unified solution to two major issues facing cosmology. This might be evidence for its existence if the observational findings from the telescope continue to hold. The proposal is elegant. A single modification to cosmology could resolve two separate puzzles. This is how physics often progresses. Unexplained phenomena accumulate until someone identifies the deeper principle that connects them. But early dark energy remains controversial. Not all physicists are convinced. Some argue the evidence is circumstantial. Others point out that early dark energy creates tensions with other observations. The debate continues. More data are needed. The James Webb Space Telescope keeps observing, adding to the evidence on both sides. What seems increasingly clear is that our understanding of the universe is incomplete. The standard model has served us well for decades, but it may be reaching its limits. The anomalies are multiplying faster than explanations, and another mystery is emerging from the data, something even stranger than the Hubble tension. Dark energy itself might be changing. Dark energy was supposed to be constant. The cosmological constant, first proposed by Einstein and later revived to explain the accelerating expansion of the universe, was assumed to have the same strength everywhere and at all times, a fixed value woven into the fabric of space itself. This assumption made the math tractable. It allowed cosmologists to build predictive models. It worked well for decades. But new observations suggest dark energy might not be constant after all. Data from multiple surveys, including the Dark Energy Spectroscopic Instrument and analyses incorporating James Webb Space Telescope observations, hint that dark energy has weakened over the past 4 to 5 billion years. If true, this discovery would overturn one of the foundational assumptions of modern cosmology. The evidence comes from measuring the expansion history of the universe with unprecedented precision. By observing how galaxies cluster at different distances, astronomers can reconstruct how fast space expanded at various epochs. The results show a curious pattern. The expansion rate in the distant past matches predictions reasonably well, But in the more recent universe, something seems off. The expansion is not accelerating as uniformly as the constant dark energy model predicts. One interpretation is that dark energy had greater strength in the past and has been gradually declining. The universe's acceleration is slowing down. The implications are profound. If dark energy continues to weaken, the accelerating expansion could eventually stop. The universe might coast to a halt. Or, depending on how dark energy evolves, expansion could even reverse. Some researchers speculate about extreme scenarios. A weakening dark energy could lead to a big crunch, where the universe collapses back on itself. Or it could transition to a big rip, where the decay of dark energy leads to increasingly violent expansion that eventually tears apart galaxies, stars, and atoms. These scenarios are speculative. The current data show only hints of variation, not definitive proof. The uncertainties are large. More observations are needed. But the mere possibility that dark energy is not constant represents a fundamental shift in cosmological thinking. For decades, physicists assumed the universe had a fixed accelerator pedal. Dark energy pushed expansion faster and faster forever. The ultimate fate of the cosmos was isolation, as galaxies receded beyond each other's horizons into eternal darkness. A variable dark energy changes this picture completely. The future becomes uncertain in ways it never was before. The James Webb Space Telescope contributes to this story indirectly. Its observations of unexpectedly mature galaxies in the early universe challenge timelines that assume constant dark energy. If dark energy was stronger or behaved differently in the early cosmos, it could explain some of the anomalies. Everything connects. The Hubble tension, the massive early galaxies, the variable dark energy. These are not separate puzzles. They are facets of a single, deeper mystery about the nature of space, time, and energy. Cosmology is entering a period of upheaval. The certainties of the past are dissolving. New physics lurks just beyond our current understanding, and the telescope keeps finding things that should not exist. Sometimes, the universe hides its most dangerous objects in plain sight. A galaxy known as Virgil appeared completely ordinary when astronomers first observed it. Sitting in the early universe, roughly 800 million years after the Big Bang, it looked like a typical young galaxy quietly forming stars. Its ultraviolet and optical light showed nothing unusual. Then, the James Webb Space Telescope revealed its true nature. Using the mid-infrared instrument, researchers penetrated deeper into the galaxy's emission than any previous telescope could reach. What they found transformed Virgil from mundane to extraordinary. Beneath its calm exterior lurked an active supermassive black hole, a monster hidden behind veils of dust and gas. The optical light showed only the galaxy's public face. The infrared light exposed its violent heart. One researcher described Virgil as having two personalities. Its ultraviolet and optical appearance showed the good side, a typical young galaxy, quietly forming stars. Its infrared emission revealed something far more extreme. This discovery has implications beyond a single galaxy. The James Webb Telescope's surveys often obtain deep imaging with near-infrared cameras, but only brief observations with mid-infrared instruments. The longer wavelengths require much more observation time to achieve the same sensitivity. This means astronomers might be systematically missing a hidden population of dust-obscured black holes, objects that look normal at shorter wavelengths, but harbor monsters at their cores. If Virgil is not unique, and statistically, it probably is not, then the early universe contained many more active black holes than current surveys suggest. These hidden giants could have played significant roles in cosmic history. They might have contributed to reionization, flooding the early universe with ionizing radiation from behind their dusty shrouds. They might explain some of the excess brightness seen in early galaxies. They might be the missing link between black hole seeds and the supermassive black holes we see today. The discovery also demonstrates the power of multi-wavelength observation. No single type of light tells the whole story. The universe looks different in ultraviolet, visible, infrared, and radio wavelengths. Each window reveals different phenomena. Before the James Webb Space Telescope, our infrared window on the distant universe was narrow and blurry. Now it is wide open, and what we see is reshaping our understanding of cosmic evolution. Virgil sits at a crucial moment in cosmic history. The universe was still clearing its primordial fog. The first major structures were assembling. Black holes were growing rapidly, consuming gas and influencing their surroundings. Understanding objects like Virgil helps us understand this transformative epoch. Every hidden black hole we find adds to the picture. Every seemingly ordinary galaxy that reveals an extraordinary secret teaches us something new. The universe is full of disguised monsters. They hide behind dust and distance, appearing innocent until the right instrument unmasks them. And Virgil is not the only surprise hiding in the data. The most distant galaxy ever discovered also held secrets that challenged everything astronomers thought they knew about the chemistry of the early universe. The most distant galaxy ever discovered should have been primitive. At a redshift of 14.3, we see this object as it existed just 290 million years after the Big Bang. The universe at that moment was a cosmic infant. The first stars had barely ignited. The first heavy elements were only beginning to form. Scientists expected to find a chaotic, metal-poor system, a jumble of hydrogen and helium, with perhaps trace amounts of heavier elements, something rough and unfinished, appropriate for the dawn of cosmic structure. Instead, the James Webb Space Telescope found oxygen, significant amounts of oxygen, enough to indicate that multiple generations of stars had already lived and died within this ancient galaxy. Enough to suggest that star formation began even earlier than anyone believed possible. This discovery requires careful explanation because its implications are staggering. Oxygen does not exist at the beginning of the universe. The Big Bang produced only the lightest elements. Hydrogen made up about 75% of primordial matter. Helium made up most of the rest. Trace amounts of lithium completed the inventory. Everything else, every element heavier than lithium, was forged inside stars. When stars burn hydrogen into helium, they release energy. When they burn helium into carbon, they release more energy. The process continues, building heavier and heavier elements until the star runs out of fuel. Massive stars end their lives in supernova explosions. These explosions scatter the heavy elements into space, seeding the gas clouds that will form the next generation of stars. Over billions of years, this cosmic recycling enriches the universe with the full periodic table of elements. Oxygen requires this process. It forms in the cores of massive stars and spreads through supernovae. Finding oxygen in a galaxy means stars have already lived and died there. The galaxy at redshift 14.3 contains enough oxygen to indicate substantial stellar processing. This is not a trace detection. The mid-infrared instrument aboard the telescope measured clear signatures of oxygen emission. The team that made this discovery used extraordinary resources. They devoted approximately 9 days of telescope time to this single object, 167 hours of near-infrared imaging, 43 hours of mid-infrared imaging, all focused on a patch of sky so small it would be covered by a grain of sand held at arm's length. They were lucky. The galaxy happened to sit in exactly the right position to be observable with the mid-infrared instrument. A fraction of a degree in any direction would have missed it. What they found challenges the timeline of cosmic chemical evolution. If this galaxy already contained significant oxygen just 290 million years after the Big Bang, then the first stars must have formed, lived, and died even earlier. Current models suggest the first stars ignited somewhere between 50 and 100 million years after the Big Bang. But those were supposed to be isolated objects, rare pioneers in a mostly empty universe. The oxygen abundance in this distant galaxy suggests star formation was already widespread and prolific. The universe was not slowly waking up. It was racing to maturity from the very beginning. One researcher described the finding as totally unexpected. The complex chemical composition, so early in cosmic history, forces revisions to models of galaxy formation. Whatever processes built this galaxy operated far faster than anyone anticipated. But chemistry is not the only surprise hiding in the early universe. The telescope has also witnessed violence on a cosmic scale, the explosive death of a massive star, captured in unprecedented detail, from an era when such events were thought to be rare. The first supernova at cosmic dawn, on March 14, 2025, a burst of high-energy radiation reached Earth. It came from impossibly far away, a gamma-ray burst, one of the most violent events in the universe,